Welcome back, everyone, to the second episode of Combinatorics. And this is going to be a problem solving session based on whatever we have done till now. As you know, we have only done two basic principles, which was mostly common sense, as we saw in the first episode. And regarding this, today we'll only be solving problems based on that. Some really good problems I've collected from multiple sources. I'll also be telling the books and stuff by the end of the session, along with what exactly do I expect from you throughout this course. The first problem, we are provided with 5 letters and we are supposed to make 3-letter words, such that in the first part, repetition is not allowed. Alright, so in order to connect you with the first episode, whatever I have told you in the first episode, I may over explain this problem a bit, so bear with it, please. We are supposed to fill 3 positions. This is our main task. Fill the 3 positions, right? And the choices that we have, A, B, C, D, and E, 5 choices, right? Now the first subtask is to fill the first position. Let's say this is the first position, this is the second, this is the third. Subtask 2 is fill the second position, and subtask 3 is fill the third. Now how many ways are there to finish subtask 1? We can fill this, we have 5 choices, right? So 5 ways. For this, since repetition is not allowed, once we have chosen something, we are left with one less option. So we'll have 4 options for this and 3 for this. And since all 3 subtasks are necessary in order to finish the main task, as we discussed in the first episode, we need to do what? We need to multiply. That is 60 ways. 60 ways in the sense 60 3-letter words can be formed with this condition. Now when repetition is allowed, the same thing. When we allow repetition, we have, for each subtask, we have equal number of choices, because we don't care if it's A, and A. We are cool with this, right? So we'll have 5 cube. That would be 125 words. I hope you have understood this. Now, one of the problems that I shared with you in the first episode itself, one of the confusions that I had regarding the monkey masters problem. What was it? We have 10 monkeys and let's say 3 masters. We had to find the number of ways such that each monkey has a master. So the main task is each monkey should have a master. None of them is left alone. Alright? Now, we say that each of the monkey has 3 choices. Let's say this is M1, M2 up till M10. Each of them have 3 choices. Now since each monkey should have a master, that means all these subtasks need to be finished. They all are necessary, right? Each of them should have, should make a choice. So we need to do what? We need to multiply. That would be 3 power 10 ways. The confusion was, why are we not saying that each master, let's say master 1, master 2 and master 3, each master has 10 choice in monkeys. 10 monkeys. And in this way, the answer would have been 10 cube instead of 3 to the power 10. What's wrong with this? The problem here is, this problem is actually analogous to the one we just did, the letter problem. I'll show you how. But first of all here, what's the problem with this approach? Let's just say master 1 chooses a monkey, master 1 chooses a monkey A. He has 10 choices, he made one of the choices, that is A. Now according to this approach, master 2 also has 10 choices, right? Including the one that has already been chosen by master 1. So can master 2 choose the same monkey that has already been chosen by master 1? That's absurd, right? This is exactly like saying, let me draw an analogy. We had 3 positions to fill from A, B, C, D and E, 5 options. What we are trying to do here in the second approach is, we said that each position has 5 options when repetition is allowed, and we ended up with 5 cube. we are basically saying that why are we not saying that each letter has 3 positions to fill? So 3 options for each letter, and that will lead to the answer 3 to the power 5 instead of 5q. So let's say A chose a position. Alright, A has 3 choices. Out of these 3, A chose a position. Now we are saying B also has 3 choices. Can B choose the same position that has already been chosen by A? As per this approach, yes, B has. And that is absurd, right? I hope you've understood that. Alright, so coming to the second problem, we are provided with a telegraph which has m arms, and each arm is capable of n distinct position, including the position of rest. Now this is very important. We are supposed to find the total number of signals that can be made. So the telegraph has m arms, let's say A1, A2 up till AM, right? Each of these has n choices, including the position of rest. So let's say rest is a position, and apart from rest there are n minus 1 more choices. Same goes for this one as well. Same goes for this one as well. Now a signal is not made when each of the arms choose the position rest. That is when we'll say there's no signal. So even if a single arm chooses a position apart from rest, we are okay with it. We are cool. We are saying that yes, that will make sure that the telegraph makes a signal. So what should we do? Should we do the multiplication stuff or the addition? We have n choices here, n here, and n here, total of, including the rest one. So should we just do n to the power m, or should we just add n m times and get what? M into n? Which one's the right part? Ask yourself, what do you mean when you're saying that even one arm choosing a position is sufficient? You're saying that the remaining, you're okay with the remaining of the arms choosing the position rest, right? Rest is being counted as a choice here as per the question. So even if the remaining arms are not doing anything, they are involuntarily choosing the position rest. So all of them are making a choice. Even if you're saying that this is sufficient, if one of the arms chooses, it's sufficient for you. It's okay. That means the remaining all of them are just at rest. They're involuntarily choosing a position. So what will we do? We'll do the multiplication principle, since each of the subtasks is like choosing some sort of action. So we'll say n to the power m, this is the total stuff. Now there will be a case when all of the arms, each of these arms, choose the position rest. And that is when no signal will be made. So that one case we'll have to subtract from here. So the answer would be n raised to power m minus 1. Sweet. Alright, so this is problem 3. Ignore the shit. This is problem 3 for us. We are supposed to find the sum of all 5-digit numbers that can be formed using 1, 2, 3, 4, and 5 if repetition is not allowed. Alright. So first of all, how many 5-digit numbers can you make using these such that repetition is not allowed? You've got 5 positions to fill and 5 choices to choose from. So for this, you'll have 5 options, right? For this, you'll have one less since repetition is not allowed. For this, 3, 2, and 1, 5 factorial. You'll multiply, right? You have to fill all the positions. Now, whenever, like, moving forward, whenever you'll have something like n choices to choose from and n positions to fill, and repetition is not allowed, you'll immediately say there are n factorial number of ways. I won't be doing this shit again and again. Alright, I'll be directly writing n factorial from now onwards. Sweet. So we can have 5 factorial, total 5-digit numbers made of these. Now how are we gonna add these? One thing that I want you to notice is that each of these positions, this one, each of these positions, can only have any one of the digits out of 1, 2, 3, 4, and 5. There wouldn't be any other digit, right? So let's just focus on one of the position. Let's say this one, all right? And whatever observation we make for this one, it will also be applicable for the rest of these. Sweet. So this will have 1, 2, 3, 4, or 5 in this. There are 5 factorial choices. There are 5 factorial numbers like this. There's a whole list of 120 numbers. Some of the numbers will start from 1, some of the numbers will start from 2, some of the numbers 3, 4, and 5. Now you should be able to observe, you should be able to visualize that there will be equal number of 5-digit numbers starting with the number 1. Repeat that again. There will be equal number of numbers, there will be equal number of 5-digit numbers starting with the digit 1, starting with the digit 2, 3, 4, and 5. Right? Total we have 120, and we have to divide them into 5 equal parts. That is 24. So there'll be 24 numbers, 24 5-digit numbers beginning with the digit 1, and there will be 24 beginning with 2, 24 beginning with 3, 4, and 5. Same is applicable for all other positions as well. For this as well, for this as well, this, and this. Now the orientation for us doesn't matter. We have to add at the end of the day. We don't care about what orientation, like in what order. We care about the digits. We have to add them, right? So we'll have 1, 1, 1, 2, 2, 2, whatever. So we'll end up adding 1 plus 2 plus 3 plus 4 plus 5. Right? Now each of these, since they appear 24 times, so we'll multiply that by 24. And since while adding, place value also matters. So for this, we'll multiply that with 10 to the power 4. For this position, with 10 cube. For the other one, 10 square, 10. And then 10 to the power 0, that is 1. That's the answer to this problem. You can repeat. There's a bit of visualization needed. So yeah, you can repeat this problem and then you can solve this one on your own. You should be able to now. If you actually understood this one, you should be able to solve. If you're not able to solve, shame on you. So you've got 4-digit numbers. You're supposed to find the sum of all 4-digit numbers obtained in all possible permutations of the digits. Now don't get intimidated by permutations. This is not a new concept you're introduced to. No. Permutations means all different sort of arrangements of these numbers. Same thing as saying total number of 4-digit numbers made of digits 1, 2, 3, and 4 such that repetition is not allowed. It's same as saying this. Alright, so all sort of arrangements of these you can make. That is what it is saying. And you have to add all those. Sweet. So now we have 4 factorial 4-digit numbers. Right? Now each of these positions can have either 1, 2, 3, and 4. And each of them will appear equal number of times. That will be this many times. That would be 3 factorial. What is 3 factorial? That's 6. So 1 plus 2 plus 3 plus 4 is the sum. Each of them appears 6 times. And then we'll multiply that with the place value. Sorry, that's 10 cube, right? 10 square plus 10 plus 1. There you are. So this was problem what? Problem 3, right? Problem 4. Sweet. Moving to problem 5. Now here we are provided with a set of natural numbers whose digits are chosen from 1, 2, 3, and 4 such that when no digits are repeated, you're supposed to find the number of elements in S, the set, and sum of all numbers in S. Now this is not like this is similar to the previous problems, but there's a bit of subtlety involved here. It says natural numbers. It doesn't say 4-digit numbers. So natural numbers can be 1-digit as well, 2-digit, 3-digit, and 4-digit. Right? Repetition is not allowed. So in one digit we'll have 1, 2, 3, and 4. In two digits we'll have two positions to fill, four options to choose from. So that would be 4 into 3, that's 12. In three digits we'll have three positions to fill, four options to choose from. That would be what? 24. Same for this, 24. You'll just end up multiplying by 1. That doesn't matter. So 24 positions, 24 possible ways. So the total number of what? The elements in S, that would be 4 plus 12 plus 24 plus 24. That's 64. So NS is 64. Now we are supposed to add these. So first of all, we'll add the one digit numbers. Let's start from here. We know this. So from the previous problem, this is what we got. We'll have 6, 1 plus 2 plus 3 plus 4 into 10 cube plus 10 square plus 10 plus 1 for the 4 digit ones. For this, how many numbers do we have? 24. Once again, we'll divide it by what? By 4. We'll end up with 6 only. And then 1 plus 2 plus 3 plus 4. Here we'll change a bit. 10 square plus 10 plus 1. We are skipping this one since these are 3 digit numbers. This was for 3 digits. This was for 4 digits. For 2 digits, we have 12 choices, 12 possible ways, and 4 digits. That is 3. So we'll be multiplying by 3. 1 plus 2 plus 3 plus 4 into 10 plus 1, 2 digit number. And for the for the single digit, we'll have what? 4 by 4 into 1 plus 2 plus 3 plus 4, 1. That's it. So you add all this, and this, and you'll end up with the answer. Now, the second part of the problem, when S is the set of up to 4 digit numbers where digits are repeated, find the number of elements in S and also find the sum of all the numbers in S. So it says 4 digit numbers are necessary, right? And digits need to be repeated. Okay, let me just get a bit of space. It doesn't really say that it's necessary to have 4 digits. It says up to 4 digits. So these are very important in combinatorics. So when S is the set of up to 4 digit numbers, that means 1 is okay, 2 is okay, 3 is okay, 4 is okay as well. Alright. Digits can be repeated. This is what it says. So 1, 2, 3, 4 in this case, there's no point of repetition here. For the 2 digits, 4 into 4 choices, 16. I hope you're able to understand this now. You should be able to understand. For this, we'll have 4 cube, and for this, we'll have 4 to the power 4. Right? Now the number of elements are going to be 4 plus 4 square plus 4 cube plus 4 to the power 4. So the number of elements comes out to be 340. That's the first part of this problem. Now we are supposed to add these. So first of all, we'll add the 4 digit numbers. So these many 4 digit numbers are possible. Each position will have 1, 2, 3, and 4 appear equal number of times. How many times? 4 to the power 4 by 4. Yes. And then we'll add this and then multiply it by the place value. This is what the sum of all 4 digit numbers possible, such that repetition is allowed. In this case, we'll have 4 cube by 4. Same thing. We'll change the place value as well. I hope you can do this now. I'm not getting further into it. Now, coming to a slightly better problem compared to the previous ones. It says among 9 factorial permutations of the digits 1, 2, 3 up till 9, consider those arrangements which have the property that if we take any 5 consecutive positions, the product of the digits in those positions is divisible by 7. Find the number of such arrangements. So this was what? Problem number 6. Alright. So we have got 9 positions, right? We have to choose 5 consecutive positions. 5 consecutive positions. Such that the product of the digits in those choices, in those 5 consecutive numbers, is divisible by 7. We don't care what number is at those positions. We only care about the positions. We need to choose 5 consecutive. So let me just take a different color. So let's say I'm choosing this one. It's 5 consecutive, right? Or I can choose this one as well. Or I can choose this one. Let me just do this. Okay. Or I can choose this one or this one. Right? Sweet. These are the 5 possible cases. 1, 2, 3, 4, and 5. 5 number of ways in which I can choose 5 consecutive positions. The condition provided is the product of the digits in those positions. Now let's say I choose this one, this, the first one. So this one, these are the 5 digits. Now whatever it is there, the product of all these 5 needs to be divisible by 7. So how can that be done? It's only possible if 7 is one of these numbers, right? Now this is not the condition for only one of the cases. You have to satisfy this for each of these. For any 5 consecutive you choose, it should be divisible by 7. So that basically means 7 should appear in all the choices, all the 5 choices, all 5 of these. So we'll have to find a common position in the 5 choices. Why? Because we'll place 7 exactly there. And then when we'll multiply all those numbers, we'll have the product as the multiple of 7. If you observe, this is the common position. This appears in all 5 choices. This as well, all these. For the first one, it ends with this position. For the fifth one, it begins with this position. Right? So we'll place 7 at the 5th position. Sweet. Now this is fixed. Now we are left with 8 positions. 8 positions. How many choices to fill it from? 8 choices. Why 8 choices? Earlier we had 9. We have already chosen 7, right? So we'll have 8 choices, 8 positions, 8 factorial ways. That's the answer. I hope you understood this, what we did here. Why was it done? You may want to repeat this. It wasn't that tough, but it's okay. Coming to problem 7. We're supposed to find the number of possible outcomes in a throw of n distinct dice in which at least one of the dice shows an odd number. So there are n distinct dices. So let's say d1, d2, up till dn. Now I hope everyone knows this. Of course you know. There are 6 outcomes possible once you throw a die. 6 here. For each of these, 6 outcomes are possible, right? Now the problem says at least one of the dice shows an odd number. It says at least. It's important. At least one of the dice. So two of them can also show an odd number. 3 of them, 4 of them, all n of them can also show an odd number. Now we'll not like try to make cases like when one die makes an odd number. Two dice, two dices out of n, you know, shows an odd number. That's stupid. In these cases, what we do is negation. We basically take the universal set, that means total number of possible outcomes, every possibility we take, and subtract what? Subtract what is not to be done as per the problem. The problem says shows at least one odd number. So we'll subtract what? Shows no odd number. Shows no odd number. So universal set, first of all, each of these have 6 like 6 outcomes, and there are n dices, so it's going to be 6 to the power n, the universal set. Now, shows no odd numbers. That means it's all even, right? Now, when you throw a dice, the even outcomes are 2, 4, and 6. There are 3. So now you don't have to choose the odd ones. You have to choose from only these 3. So each of the n dices now have three possible choices to make. That would be what? 3 to the power n now. So we have to subtract this thing. This is the answer for you. I hope you understood negation. We have done a problem on negation in the previous episode as well. Anyways. Alright, so problem 8 for today. We're given that 33 factorial is divisible by 2 to the power n, and we're supposed to find the maximum value of n. Sweet. So 33 factorials. So that would be 33 into 32 into 31, like that. 3 into 2 into 1, right? So how many of these are going to be multiples of 2? We'll have to count the multiples of 2. How many of them? So 2, 4, 6, 8, 10, like that. 16 numbers. They're going to be 16 multiples, right? We have to count the powers of 2, right? That's why we are doing this. Now, what about multiples of 4? Why are we doing this? Multiples of 4? Because they will give an extra power of 2, right? We have counted 2 only one time here in these. They have been counted in this as well. But 2 has been counted only once here. So we'll have to count that extra here. Like this is 2 into 2, right? So this extra 2 we haven't counted. That is why we are checking multiple of 4. So that is 4, 8, 16. Okay, 12, 16, 20, 24. What else? 28 and 32. How many of these? 1, 2, 3, 4, 5, 6, 7, 8. 8 extra 2s. Similarly, multiple of 8. So 8, 16, 24, 32. That is 4. This will also give 1 extra 2. So 4 extra 2s we got. So multiple of 16 now. So 16, 32. 2 extra 2s. Now multiple of 32, which is basically 2 power 5. So 1 more extra 2. Alright? 1. Sweet. So how many 2s have we got here? 16 plus 8 plus 4 plus 2 plus 1. How much is that? Whatever. 1, 3, 7, 8, 7, 15. That is 31. That is the answer to this problem. Alright, so coming to problem 9 of this. We are supposed to find the number of times the digit 5 will be written when listing integers from 1 to 1000. So 1000 doesn't really have 5 clearly. So we'll be ignoring that. We'll be mostly dealing with 3 digits, 3 positions to fill. Now you may wonder, what about 2-digit numbers or a single digit number? So we can always write a single digit number, let's say 4, as 004. So we are basically allowing 0 in these positions. Alright, so that will make sure that single digit numbers as well as 2-digit numbers also get counted. Sweet. Now the case 1 here is 5 appears only once. So in these 3 positions. Now in this case, there are going to be subcases. 5 first occupies this position. The second one would be 5 occupies this, or 5 occupies this. Sweet. What about these positions? We have said 5 appears only once, so 5 cannot appear anymore. But other digits can be repeated. There's no such constraint. Like we are cool with 544. What we are not cool with is 554. Alright. So the choices that we have to make it from 0, 1, 2, 3 up to 9. There are 10 choices to make from. We have already chosen 5, so we have 9 choices left. For this as well, 9 choices. So 81 here. Same for this, 9, 9, 81. Same for this, 9, 9, 81. So 81 into 3, that is 243. There are 243 numbers from 1 to 1000 in which 5 appears once. We have to count the number of times 5 appears. So 243 times in the first case. Now, talking about the second case, 5 appears twice. Now we'll have to multiply the answer that we find by 2 because we have to count the number of 5s, right? So the case 1 here would be, the sub case 1 would be 5 5 blank blank 5 5 5 blank 5, right? Now for this position to fill, we'll have how many choices? 9. For this as well 9, and for this as well 9. In total there are going to be 27 choices. So there are 27 numbers from 1 to 1000 in which 5 appears twice. That means 5 appears how many times? 54 times. Here 243 times, here 54 times. And there will be one case of 5 5 5. There's just one case. So here 5 appears thrice. So the total number of 5s going to be 243 plus 54 plus 3, that is 300. That is the answer. Alright, so coming to the problem 10 of this, we have an application of, a bit of an application of the floor function. It's denoted like this. Alright, there's some number here. This is also referred as the greatest integer function. Let me first define this for those who don't know. So if I'm writing this thing, floor function, this basically gives the maximum value from the set S, from the set of integers actually. Let's say any alpha belonging to the set of integers such that alpha is less than or equal to x. What is x? Of which we are trying to find the GIF of. Alright, so what does this mean? Let's say I have to find the GIF of 2025.2025. Big number. According to our definition, we have maximum of what? All the alphas belonging to the set of integers such that alpha is less than or equal to this thing. So alpha needs to be what? Integer. It belongs to the set of integers and it should be less than or equal to this thing. So the integer is less than this thing, that is 2025, 24, 2023, right? Up till negative infinite. This is the set. We are saying maximum of this, maximum of this is 2025. So the GIF of that is 2025.2025 is equals to 2025. Now what if I had negative 2023.01? Now we have negative. Once again the same definition, maximum of all the alphas belonging to the set of integers such that alpha is less than or equal to negative 2023.2023, sorry, 01. So alpha is an integer and it's less than this or equal to. No, it cannot be equal to, right? Because this is not an integer itself. So an integer less than this is going to be 2024, negative 2025, negative 2026, like that. The maximum of that is this. So this is going to be 2024. I hope you have understood greatest integer function. Now, since we are talking about greatest integer function, let me also tell you that in the upcoming week or so, couple of days, you'll be getting a one shot, a very comprehensive lecture, comprehensive, on the greatest integer function, the ceiling function, the floor function, the least integer function, which is the ceiling function, this thing, and the fractional part function, this thing, and the nearest integer function. So this whole family of integer functions, this thing. All right. So you'll get around 5 to 6 hours long lecture based on this. There are absolutely no prerequisites. What we'll discuss is all sorts of applications. From limits, you don't need to know like calculus and limits and stuff in order to attend this session. Everything, as I said, there's zero prerequisites. So limits, integration based problems, sequences, series, involving GIF and all these things. Every sort of problems that are possible through these. So that is what we'll be doing in a couple of days. Make sure to watch that. Anyways, coming to our problem now. So E is basically this thing. Wow. I want you to understand that once, let me just draw a number line. This is 1, this is 2, this is -1. So if there is a number here, its greatest integer function is always going to be 0. If a number is less than 1, its greatest integer function is going to be 0. Like less than 1 but greater than 0, alright? Greater than or equal to 0. Its greatest integer function is going to be 0. Here if you see, what is it? 53 by 150. What is this? This is less than 1. So this is going to be 0. Same for this. Same for this. Up till when? Until we don't get 150 by 150, we'll keep getting 0. So when will we get 150 by 150? When we get 50 plus 100 by 150, right? So from here 1 by 3 is fixed here. So 1 by 3 plus when we get 33 by 50 here, so we'll have 50 plus 99 by 150. This will still be less than 1, so this will be 0. So up till the 33rd term, we'll keep getting 0. Once we reach the 34th one, we'll have something bigger than 150 and by 150. That will be greater than 1. Once I get something greater than 1, less than 2, x is greater than 1 and less than 2, the greatest integer function would be what? 1. Then up till the 50th term, the GIF would be 1. So 0, 0, 0, 0, 0 plus 0 plus 0 up till what? 33 terms. And then plus 1 plus 1 plus 1 for what? How many terms? 17 terms. So E is going to be 17. That is the value of E. Now we are not supposed to find the value of E. The problem says find the exponent of 2 in E factorial. Now this is like the previous problem. So you have to find the exponent of 2 in 17 factorial. I hope you can do this now, since we have already done this in probably problem 8 or something. Yeah, that exact thing you have. So yeah. Alright, so coming to problem 11. Wow, problem 11. It says that integers from 1 to 1000 are written in order around a circle, starting at 1. Every 15th number is marked 1, 16, 31, etc. This process is continued until a number is reached which has already been marked. Then find the number of all unmarked numbers. Find the all. Okay, it basically says find the number of all unmarked numbers. All right. Okay. Now before we get into this problem, I want you to imagine a clock, right? So here we have 12, we have 6 here, we have 3, and then we have 9. The hand of the clock, the hour hand, at first is at 12. So you are at 12. Now I ask you to move 9 hours ahead. So from here you started moving. Where will you reach? You'll reach 9, right? From 12 to 9. Now once again, now you mark this point, marked. Now once again I said, move again, 9 hours ahead. Now where will you go? So 9 plus 3 is 12. So 12 plus 6, you'll reach 6. You mark this. Now once again I say, move 9 hours ahead. Now 6 plus 6 is 12. Plus 3, you'll reach 3. Mark it. And once again I say, move 9 hours ahead. So 3 plus 9, that is 12. Now stop. You have reached somewhere which was already marked point. You started from here, right? So 4 marked points. So after 4 laps, like 4 such, performing this process 4 times, you reached the spot where you began from. Why did it happen? In total, you covered 36 hours, right? 4 times 9. Why did you reach the original position once you finished 36 hours? That's because 12 divides 36 and 9 also divides 36. It's because 36 is the LCM of 12 and 9. That is exactly what you need to do here in this problem. You basically have a clock on which there are 1000 marks, 1, 2, 3, like that. Earlier the gap was 9, this time the gap is 15, every 15th number. And there are a total of 1000 numbers. Earlier there were 12 numbers. What did you do? The repetition happened. You reached a point, the original position, at the LCM of these two. Exactly like that, we'll have to find the LCM of these two. I hope you've understood the logic behind why we are doing the LCM thing. The LCM will come out to be what? 3000, right? Now, how many marks? So 3000. Now, the number of marked points, if you see, marked points, here in this case, that was 4, right? You basically stopped at every 9 gap. So you basically divided 36 with 9. That is exactly what we'll do here. So 3000 by 15, that's 200. So you will stop at 200 such points. And the moment you stop, you'll mark that point, right? So number of marked points would be 200. Total number of points is 1000. Number of marked points is 200. Number of unmarked would be 800. That is the answer. This was a very easy problem. Now, whenever you see, because these things are very common in combinatorics problems, don't get confused. Use this logic, the clock logic. All right? Whenever you encounter such kind of stuff. There are people doing it using AP as well, AP and stuff. That is a really ugly method to do. But okay, that also gives you the answer. So, anyways. All right, so coming to problem 12, I guess, right? Wait a minute. Yeah. We are provided with a set, numbers 1 to 10. We are supposed to find the number of subsets A of S such that if X belongs to A and 2X belongs to S, this implies that 2X belongs to A as well. Wow. First of all, subset. What is a subset? So let's say we have a set S. Let's consider this one as well. Alright, so coming to problem 12, I guess, right? So we are provided with a set and we are supposed to find the number of subsets of the set S such that if X belongs to A and 2X belongs to S, this implies that 2X belongs to A. Now there are kids watching these videos as well, so what is a subset? So let's take this example. So S is 1, 2, 3, 4, 5. I'm not going up till 10. So the subset of a set is any set whose elements are also a part of this. What does that mean? So let's say I take 1, 2. This is a subset of S. Why? Because all the elements of the subset belong, like, are also an element of the main set. If I say 1, 2, 6, this is not a subset. Why? Because 6, an element of the subset, but is not an element of the main set. So that is what a subset means. So it can be 1 as well, 2 as well, 1, 2, 3 as well, 1, 2, 3, 4, 5 as well. Right? So there can be empty as well. Phi is also a subset of every set. So I hope you have that much of an idea. So the condition here is very interesting. It says if X is an element of A, so there's some set A. Let's take any set. Forget the problem for now. Let's take any set. 1, 2, 3. We're saying if X belongs to A, any of the element, let's choose X equals to 2. So it says if X belongs to A, it does, and 2X belongs to S. Now we'll check. Does 2X belongs to S? Does 4 belongs to S? It does. Then this implies that 4 should also be in A. Is it in A? No, it is not. That means this is the wrong subset we have formed. I hope this is clear now. So you cannot choose 1, 2. Why? Because for x equals to 2, if you check, 2x is 4. 4 belongs to S. Now if 4 belongs to S, it should also belong to A. But it does not, so this is not a right set. So once you have chosen 1, you have no other option. You'll have to choose 2 as well. Once you have chosen 2 now, you have to choose 4 as well. Once you have chosen 4, you'll have to choose 8 as well. Now do you have to choose 16 now? You'll check 8 into 2 is 16. Does 16 belongs to S? No, it does not, so you don't need to. This is a valid subset A for this problem I'm talking about. Second valid, 3 if I choose, then 6. I won't go further because 12 of course is not a part of S. Third, 5, 10. And then 7 itself, 7 alone. I don't need to add 14, right? And then 9. Sweet, all of the numbers we have got. So 5 cases we got, these 5. Now, further, 1, 2, 4 and 8. We have got 3, 6. We have got 5, 10. We have got 7 and 9. Now from here, we can make more subsets. Can we say 1, 2? We cannot. We have already discussed that. Can we say 2, 4? We cannot. Can we say 2, 4 and 8? We can. Can we say 4, 8? Yes, we can. Can we say 5? Yes. So 1, 2, 3 and 4. Sweet. From here, 5 always counted. This is a subset of every set, so it's counted. Can I say 3 alone? No, I cannot, because 6 belongs to S. Can I say 6 alone? Yes, I can. Why? Because 12 does not belong to S, so I can write it here. So two choices, 1 and 2, 5 and 6. Similarly, here 5 and 10. Here I'll have 5, 5. Alright, now, from here I got how many choices? 1, 2, 3, 4. 4. No, wait a minute. 1, 2, 3, and 4. Am I missing something? Yes, I can write 8 alone as well. Right? So I'll have 5 choices. Here I'm getting 1, 2, and 3. 1, 2, and 3. So 3. Here I'm getting once again 1, 2, and 3. Here as well 2. Here 2. Now, what to do? Can I not make merger of these two sets? Like, can I not mix these? Like 1, 2, 4, 8, 3, 6. I can, right? I can, right? No condition is getting violated. I can merge all of them together, some of them together. That will also be a valid subset. So what to do now? For this patch, we have 5 options getting. From this, we have 3. From this, we have 3, 2, and 2. We'll use the multiplication principle. Why? We'll simply do 5, 3, 3, 2, 2. That is 180. But why? Like, choosing any of these is sufficient. We are saying choosing any of the subsets is sufficient. It's following the condition. Why do we need to use the multiplication principle? Once again, it's exactly like that rest case, the telegraph problem. The rest cases also included phi is being included in all of them. So when you're saying that I'm comfortable with 1, 2, 4, 8 alone, like this is also sufficient, you're basically saying Rest others, all these other patches are making the choice 5. So they are involuntarily making a choice. That is why we are using the multiplication principle. So that the answer to this problem, 180. I hope you have understood this. This was a good problem. Sweet. All right, so really good problem. This is problem what? 13? Okay. Was it 13? Yes. We're supposed to determine the maximum among all numbers obtained by deleting 100 digits from this number, whose digits are the integers 1 through 100 in order from left to right. What does this mean? As you can see, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, like that. So it has been written in that order. So that is how this number has been made. All right. So first of all, how many digits? Nah. All right. So coming to problem 13, right? It says determine the maximum among all numbers obtained by deleting 100 digits from the number this. Wow. Whose digits are the integers 1 through 100 in order from left to right. Left to right. So it's basically the counting written like a single number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like this. Alright, so this may be a bit confusing, but once you observe this, it's easy. Now, first of all, how many digits does this number has? So at first, 9 single digit numbers, right? And then from 10 to 99, there are going to be how many numbers? 99 minus 10 plus 1, that is 90. These many 2-digit numbers, and 100 is a single 3-digit number. So in total, we are going to have 9 plus 2 into 90 plus 3. How much is that? 192 digits. This number has 192 digits. The problem says you're supposed to delete 100 digits from the number. So once you delete 100 digits, you'll be left with 92 digits. Now in all these, like in all possible arrangements, you have to determine the maximum of it. All right. So you have like 92 digit numbers at first. The observation you need to make here, something you need to think on your own, that in order to get a maximum number, you need to have as many nines in the beginning as possible. The more the nines you have, the better it is for you, right? So the number basically is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, I'm not writing the whole thing. Don't worry. So in order to get the first 9, I'll have to delete this thing, right? In order to get the second 9, I'll have to delete this whole thing till here. So for the first 9, I deleted how many numbers? 8 numbers got deleted. For the second 9, how many numbers? 10, 2, like 10, 11, 12, 18, and 1. Right, so this is 19 digits. This got deleted. Once again, the next chain here will have 20, right? So from 20, 21, 22 to 28 to 2, we'll leave the 9, will not delete the 9. So once again, 19 digits will delete. So 19 more got deleted. So now the next chain is 30, 31, 32, and 383. We won't delete the 9. So once again, 19 more digits. So 19 more. Now 40, 41, 42. So we'll have 48, 4, 9 we won't delete. So 19 digits more. So till now we have deleted 19 into 4 plus 8. How much is that? 84 digits. Now we cannot delete the whole chain now, because the whole chain consists of 19 digits and we are left with 16 digits to delete, right? We can only delete 16 digits now. Now what? So now you may think that just delete the next 16, like the, the 16 digits in the next chain, like, and write 9999. So how many have we got? Five nines, right? And then 58596061 and continue. I deleted 16 from here, 16 digits in the next chain. In 50, 51, 52, up till 57 I deleted. And I got this. This was wrong. Why? Because after 9, the next number should be 8 in order to maximize our result. But we cannot choose 8. Why? I'll tell you later. But we can choose 7. This should be our priority. What do we have? 5. We need what? 7. So we have got 999, 5 nines. What we'll do is we'll delete everything from 51, 52, 53, 54, 55, 56, and 5 till here. We'll leave 7. Alright? So 7 and then 5, 8. We'll leave 7 here. How many digits is this? 2 plus 2. That's okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. What else? We can delete this 5 as well. We don't care. Right? So we deleted this as well. So 9, 9, 9, 7, 8, and then 5, 9. Now we can continue. Now why couldn't we delete 8? If you observe here in the chain 50, 51, 52, 53, 54, 55, 56, 57, 58. If you deleted all this in order to get an 8, this would have been 17 digits, while you had the option to delete only 16 of them. Is that clear? So this will be the required answer for you. This is the maximum number. This problem is more about your visualization. The better you can think, the better it is for you. So you may want to repeat everything that has been said in this problem. This was a really good problem. Alright, so that is a wrap up to this session, and we'll be solving more problems in the second part of this as well. Um, and as I said, I'll be telling you the sources and stuff from where I'm taking the problems. So these are the sources. Now you don't need to like download the PDFs of these and start solving and stuff, because all the solved examples as well as the problems given in the exercises are being solved in the lectures itself. So I'm not leaving anything. But you can practice Pathfinder because there are a lot of problems. So for practice purposes, the best ones I have already picked from this, but you can solve for like practice. And apart from that, what I expect from you is just attend the lectures, solve all the problems that are being given in the lectures. That's ample.